center. It's all the technical part. So there is an echo. I think I have to turn off here. Can you hear me? It's okay? Yeah. So here I have I can't see myself back. So. Yes. Microphone is really off. Yeah. Okay, so yeah, the microphone is off. On. Can you hear me better?
I think now it will be fine for on.
Okay. Can you hear me?
No issues.
Okay. So I will give a little bit of a presentation of the University of Delft. That's the University of Technology and the Faculty of Aerospace Engineering. Then I want to do a very quick review of the different research activities. So it would be a really short overview because I don't go into detail too much, but so that in the next 4 days I will be here until Thursday. If you see any topic you would like to interact more and so on, we can do. And then look to the future. So let's start with the introduction of the faculty of the Delft University of Technology and our faculty. So Delft University of Technology is in the Netherlands. You see here a picture of our library. So this is the external building of the library. And usually you do not have this weather in the Netherlands. It's not like here. So, but this is sometimes you can have. So the university is quite large. Have not so large as here, but have different bachelor program, master program. We have a faculty. So aerospace is a faculty in our case. We have about 4,000 students, PhD, and different alumni. So these are number, I think, of one. So I got this case about 1 year ago, so it can be a little bit changed. So as I said, aerospace engineering is one, the faculty, and this is the building, so the large building and here, and then we have some labs on the other side. So we have a different bachelor and a master student, about 122 scientific staff, and are growing more, support staff, and it's really international. So these are some numbers of the people. So we have many students from India, both with master and as a PhD student. So TUDELFT is the university, Delft University of Technology, that is shortened is TUDELFT, is ranked as a 10 in the last years from QS World University ranking for engineering and technology. But if you go on the really topic, so in mechanical, aeronautical, and manufacturing engineering, we were last year's fifth one. So if you consider that UK now is outside Europe, have the US, we are the one in Europe. What we we have structures in the teaching that is called like a T-shaped structures. So we have the bachelor's course that's 3 years, and it's really going to the different topic of aerospace, so in a more broad way. So there are some fundamental sciences, professional skills. There is a lot of teamwork on the class from the first year to the third one. And then students want to go in the master. In the master, they have to decide which topic they want to go into. And so they have a aerospace specialization, but also professional orientation, and there is a master thesis at the end. It is a really almost 1 year, so it's quite a amount of work during the thesis. The faculty is divided in the departments. So there is a department of space engineering, a control operation, aerodynamics, wind energy, flight performance propulsion, and aerospace structures and material to which down. Then the departments are divided in research group, different research groups, and we belong to aerospace structures and materials, in particular to aerospace structures and computation mechanics, but there are also groups on materials, on structural integrity, and on manufacturing. But if you look slide, it cover really the topic of different fields, all the fields of aerospace. And also not only aerospace, because there is a large, for example, group now in wind energy. This is a photo of our lab. So yes, see in November. It is a little bit maybe not the last update photos, but we have a lot of testing equipment on this side that you cannot see, but it's here is more a composite lab and manufacturing structures. We have also a manufacturing laboratory here, and here is the mechanical test NDT lab. We have also physics lab. We have a quite good testing equipment. I think I can this because she already gave a longer presentation about me, so I will skip that one. But I cannot, before presenting my presentation, I cannot say that all the work that I present is thanks to my students. So the group of students is changing because some graduated, and a new one, and so on. So these are some, not maybe not the last updated one, but what I want to show is that these are really quite an international group of students. Some are and so really international and of their and these are some of the funding I have in this moment. So a lot of funding of that you will see is given by the European Commission, the European Commission, and as a special program, which is Clean Sky 2, and now the new one, Clean Aviation. There's some funding from the Air Force Lab in the US. Fokker, that is an airplane manufacturer, and the most one in the Netherlands, and now it's called GKN Fokker. Some Dutch government, and also some research in education. Yes, we need that to put there. So next time we must have that. Good. I'm ready. I'm ready to put your logo, of course. So it's good. Yeah. So yes. So after this.
We are not able to hear you. You are on mute. Can you please unmute?
Hello, yeah.
We are unable to hear you. We are unable to hear you. Can you please unmute?
Besides that, institute also supports, there are several chair positions, like Infosys chair position, Satish Dhawan chair position, and there is a Christian, there is a Pratiksha Trust, which supports three visiting professor in neuromorphic computing. So these all details are on our website. So feel free to reach me or our office if you have any difficulty or any anywhere where we can be of any help. We're more than happy to do that. Once again, wish you all a very wonderful workshop and hope this will attract again, from my perspective and institute perspective, more students, more faculty exchange, and of course, do some great science together. Okay, thank you so much.
Thank you. Thanks again for the welcome, and we hope to increase the collaboration. So in these days, we have 4 days to really talk about all these possible activities. And this is what I was trying to present, a little bit a quick overview of different topic we are working. So this is inside one of the European projects, so call it Sostenere. You can look at the web page if you want more details. And we are working on materials, but more towards sustainability. So some of the aspects I already mentioned before about the thermoplastic, so working how a thermoplastic can be used, and also what we call it the second life. But also we are exploring some capability of the thermoset to work in the second life. And also in this project has some joint between different materials. So for example, between a composite and metals. So we use this technology that is not very clear here, but there are small pins to join the two parts. And also how not only which are the characteristics and how they can improve the welding towards the welding in the case of thermoplastic, but this joint between composite and metals with the pin towards a certification. And because of the circular economy and so we use as a second life material, but also how to disassemble this welding to have use them again during a new rebuilt structures. So here are some of the structures that we are testing in our lab, and also the DIC view of the single lap shear joint. As you can see, a lot of other activities is on thermoplastic, and this is another European project that is called Stunning. This is funded by Clean Sky too, that is inside the European Commission, and is going towards to manufacturing a large thermoplastic fuselage that you have seen during your visit. So this is a really large thermoplastic single-aisle aircraft. And the skin, they said that is the largest single piece on thermoplastic built up to now. So it's been manufactured by NLR, the Dutch Aerospace Center, and then there are the stringers that are welded, in conduction welded on the skin. So this has been mainly a demonstrator for the manufacturing technology. Then there has been put as the cargo floor, all the frames and so on. And then there is this has been built in the Netherlands and also in assembly in Delft. But then has been sent to Germany to build the upper part from a little bit different technology of thermoplastic, and will be assembling the two parts, the upper and the lower part of the fuselage at Airbus. What I'm more working is to consider the characteristic of the welding in stiffness panel. One of my main research areas is on buckling. So we investigate the areas that are more subjected to possible buckling. And you can see here, and from that we investigate the fuselage deformation, but from that we took a characteristic panel, that is a 3-stringer panel, so quite large, that was manufactured exactly with the same technology, so that we could investigate, and you can see here a little bit the conduction welding of the omega-shaped stringers. And we tested, and you see there the failure mode.
What is the explanation of stunning here? It's quite
Stunning? Whether stunning? Oh, this is the difficult question. Something like smart technology, innovation, fuselage, multifunctional fuselage, something like that. Yeah, yeah. We use acronym because nobody remembers the long time. But this welded is not the only way to join thermoplastic composites. And this is another technology that is patented by Fokker. And he's called it the butt joint technology for joint different thermoplastic parts. The advantage is that they can really manufacturing independently the skin, the web and the cap, and then join them with this butt joint as a filler here. But especially can be joined as on curvature panels. So this was a study on the flat panels, but we tested as curvature panel, and this can be as to manufacture double curvature panels, and in that case, you can stiffness independently the stiffness there on a level curvature. So you can see, as in this case, we wanted to investigate the buckling phenomena and how buckling, this is because of the joint technology, this can be a weak area. So we wanted to see after in compression, testing in compression, the buckling of the structures, of course, make it a weaker part for the solicitate the part where the separation between the skin and the stringers. So we wanted to see the skin stringer separation under compression after buckling. And you see that we were doing finite element, but also the test, and we predict both the buckling, the post-buckling, and also the failure. And you see two different panels that we tested, nominally identical, but there was some imperfection, and so a little bit difference between the two tests in the post-buckling field. But the correlation with the finite element analysis was pretty good. This is another research. This was funded by the, finished a couple of years, 1 year ago. Was funded by the Office of Naval Research. And it's always related to buckling, but in fatigue. So we tested and analyzed a single stringer, we call it single stringer specimen. This was done in thermoset. But the problem is that if you test in fatigue, you have this an area of the skin stringer separation. But this area of skin stringer separation is in fatigue is very connected to what happened locally. So all finite element code up to now introduce the global load, global ratio for the fatigue. But global ratio is the load that you apply, is the ratio that you apply in fatigue. So if you think about the test in tensile, it works well because you apply maximum load, minimum load, maximum load, and minimum load. What happens locally is the same of the load that you apply globally. In this case, it's different because you apply compression, so the structure have a maximum load and a minimum load. But what happens locally is not the same because you have this possible failure and you have the expansion of the failure. So what is happening locally is changed continuously. So if you apply, because of the buckling shape and the repeated loading, so if you apply the global ratio, that is not taking what applied locally. So to do that, to try to investigate that, we created two different models. So we created one model, a parallel model.
Ma'am, I can't hear.
We can't hear your voice. Is
So here you see the numerical and the experimental correlation and the propagation in pre-damage between the skin and the stringer separation. So another activities always related to buckling, but a little bit different. So if you test like a single stringer, because it's cheaper than testing a really large panels because of cost of manufacturing and testing, is really representative of the structures, but you should test a lot of these specimens because the buckling mode can change because of the imperfection. So one single stringer, like we saw that one before, can buckle in 3 half wave or 2 half wave. It can be buckled in this direction or both of them like that. So represented the large panel, you have a quite variability because of the imperfection. So you need to test many of them. So to be able to reproduce the buckling shape and to be able to reproduce the most
Hello, ma'am. I can't hear.
So there is experimental and numerical result. So we investigated from a large panel, which is the area that is most critical and which is the buckling shape that is most critical. We tested DCB, ENF, and ECT for getting the material properties. And then we use material properties and we reproduce the area that is more critical, and we reproduce the buckling shape that are identified as the most critical, and then we investigate the skin stringer separation.
Numerical models are along with the imperfection.
Sorry?
Numerical models are along with the imperfection.
Yeah. Sometimes we put the imperfection, so we measure the imperfection, and then we put the imperfections there inside. Yeah, depending on which phase we are. So at the beginning, if we study a panel and we do not have yet, we put an imperfection that are the eigenvalue, but when we have the panel, like in the test before and so on, we measure imperfection and we put them together. Yeah. And you will see us in the next presentation. Another work for a PhD that just graduated a couple of months ago was about thermomechanical buckling of aerospace structures. So buckling not only driven by mechanical load like compression or shear, but also driven by thermal loading. So the idea is as for a supersonic aircraft, because you have already the thermal loading there. But we investigate both analytically, numerically, and as experimentally. Jumping. So how the thermal loads can change the buckling shape at one point. So for example, here you see that go from one half wave to half wave. And the idea is to use this mode jumping to adapt to have a shape change in the aircraft, as you will see a little bit later. I'm giving, as I said, a little bit an overview just so that we can talk more in the next days, but so up here we give more in-depth presentation. So in other activities I'm doing mainly with NASA Langley and NASA Marshall. It's about no. Yes. Can you admit? Okay. So speaker on.
Can you hear me? Yeah.
Yeah.
Speaker should be on.
This is off.
Speaker is on. My person can hear it. Yes,
To me, it's okay. I don't know if it's for them it's okay. Is this my Yeah, you can. So, team, you want on or off?
Off.
Try like this. Okay. Still a little bit. So this is about the scaling of the structures. So we develop a methodology to scaling really the large structures analytically, and based on non-dimensional buckling equation. And from that, we also built the numerical model, and at NASA, they manufactured the shell, reduced shell structures. So we did the test, a couple of, some tests was done in September, some tests were done before COVID, still thinking when they were done. And we tested them, and so we had the result, experimental result, to see the correlation between experimental, numerical, and analytical, but also between this smaller scale to the real scale of the larger structures. A little bit different research is always on cylindrical shells, but with the technology that is called variable stiffness. So, because you see that the fiber, this is a cylinder that is called made traditionally by different ply, lay up in a different ply. But this is another way to manufacture structures in composite. It's called the variable stiffness. So you have a toe of fibers that you can change the layout, the orientation in the same layout and the same ply. So you change the orientation and you can distribute the stress around the structures. So if you can see this go from this and going down and like that, so we can change the stiffness in the different location of the structures. So to create some decrease the stress concentration in some area and so on. So we did apply to cylindrical shell, we did the test, and also the vibration correlation techniques. That is a technology to measure the natural frequency of the structures before, but also during the loading. So at that moment, measuring how the frequency of the structures change during the applying the compression load, you are able to estimate, to extrapolate the buckling load before you arrive to the buckling. So you do not need to reach buckling, especially in the case when buckling is a failure, but you can predict the buckling during the test and loading it at about the 50 or 60% of the buckling load. One of the work that we are doing with a postdoc that is, she's Indian and was in my group for 2 years with the funding from the European Commission and Marie Curie Fellowship, is a project called Macadamia, but don't ask me what the long acronyms, but it's mainly to use nanotubes, interleaves to increase the characteristic really of the interface between the different parts of the composite. And in particular, we put that in a T shape. We put some interleaves with a nanotube to increase the characteristic, especially in a pull-out, but also on DCB tests. We did perform a DCB test and how the fracture toughness changing. So this is something that I know that you are working on, and if you want, we can discuss a little bit later. But it's been done both experimentally and also in this case numerically. One of the last one, I work at on crashworthiness, so another area on crashworthiness. And so inside the same project of before, the stunning project, you see here again the same fuselage. We were investigating not only the buckling behavior, but also the crashworthiness of this thermoplastic new configuration of fuselage. We did the crash of the lower part under the cargo floor, but especially we saw that one of the weaker part was the joint due to the welding of this strut to the cargo floor and to the frames. So we reproduced this part and we tested the welded, and Javier did all these tests of analysis. So from one side, for investigate the crashworthiness, we tested the welding, how they work in static and dynamic loading, but also we reproduce with meta models the energy absorption of the structures in the thermoplastic fuselage. And related to this, so not only crash, really crash on a solid surface, on a hard surface, but also on water. This is a test up at Politecnico di Milano. We performed some tests on impact on water of composite panels, both flat and curved panels. So we correlated, we used different techniques. This is SPH and Euler-Lagrangian technique to investigate how is the deformation during the impact on water. This is the last one because it's connected us about the future. So I had a student that together we investigate how buckling can be used to change the shape of structures of a wing. So we wanted to use buckling to change the use inside the structures, but mainly to change the stiffness of the structures. And in that case, we can change and having a change of the shape and having an adaptive wing due to the buckling of some internal part. So having not only one bistable configuration, but also multi-stable. So this was a little bit an overview of the different activities. And I want to go and give you a look a little bit on the future. So most of these research are still ongoing. Some of them just finished, but the topic I'm working, as you see, a different aspect of composite structures. But one of the large projects that I got just funded is the so-called ERC Advanced Grant. That is a quite prestigious grant in Europe. Prestigious because they give a lot of funds. Post-buckling, paneling post-buckling, you have a linear part. This is a simplification. You have a buckling and you have a post-buckling there. This is a part of the wing in compression that we saw before. And the traditional approach is merely to design until the buckling load. What I want to do is not only using the entire post-buckling field, but also having really designed for post-buckling and having using the different post-buckling shape. So the goal is to develop the new concept of adaptive buckling-driven structures for the next generation of the aircraft, and having to apply for adaptive structure for aircraft. So what I will do, one of my main area in the next 5 years, will be really to work on this, but working on both analytically, numerically, and experimental, always in the combination, but also going in a little bit more on increasing complexity. So starting from the panel that we saw before and using this possibility to explore multi-stable configuration, then applying a wing box to change the shape, and then let's see how far we can go. But the idea is to have a morphing adaptive wing. So this is a project long-term in 5 years. And this grant, call it high gain, high risk, because so here the risk is, let's see how far we can go. But at least for urban mobility and so on, we can probably apply. So this is one of the things that I will more work in the next years. But I saw what, now I will surprise Dinesh if you have not yet told him. So I start my career at, you have heard before, from Polytechnic. No. It's good. I start my career, I say, in the last century, but not 2 centuries ago, no. No. So I started my career at the Politecnico di Milano, where I got a master and a PhD, and so Dinesh came and visited a few years ago. During the time, I was visiting both, as you heard, at MIT, visiting professor there, and I had also spent a period in China at Tongji University in Shanghai as a visiting professor. Then I started to travel too much, maybe. So as you heard, I went to University of California, San Diego, for a few years, almost 2.5 years there. Then San Diego is beautiful, so don't say anything, it's my heart, but it's a little bit far. So it was too far from everything from Europe. So I accepted a position at TU Delft, and I'm there since more than 8 years now. So the thing is that I've decided to go, to go back. So I feel a little to go back to Politecnico di Milano. So, and this you can see will happen quite soon. So I'll surprise you, but I will keep a visiting guest position at TU Delft. But at the end, I decided to go back to Italy for several reasons, and was done as a little bit in a hurry because of the grant that I showed you before that have to start in May. So it cannot be postponed anymore and can be moved to university. So I said, this is my moment to go back to my country. So I hope we can investigate the collaboration with.
Both are my second homes, Delft.
Yeah, I know. So next time maybe we have to hear 3 different of the different countries. So yes, so I will keep in any case the guest position at TU Delft, but also I will start back in my home countries in Italy soon. So I hope we can continue in any case to work together. So that's all. I thank you for your attention. Here my QR code. The web page is a little bit not updated. I need to work on that. I had no time in the past few months, so you see there as a link of the papers and so on, but not the last one. I will try to update it as soon as possible. But thanks again for the invitation, and thanks for everything. Thanks. I don't know if you have any question now, because I went as a little bit long.
No, I think we had interruptions as well. So.
Yeah, I don't know. Any question now?
Any quick questions?
Or in any case, I will be here for days. So.
In one of your slides, you were mentioning about vibration test in a hanging position.
So this, I think we were. Wait. This one. Yeah. Yeah. So we tested this structure for 2 reasons. One, because we wanted to investigate the fiber variable stiffness structure, so how this different methodology was there. But also we wanted to test a different technology, how to correlate the vibration with the buckling. So we tested first in pure compression. and we did the buckling. This is a composite, so it's elastic, and we could test several times. Then we tested the structures, really natural fibers, so hang it and so on, the natural fiber, natural frequency, so really to study the vibration of the structures independently. Then what we did is this vibration correlation technique. So we put the cylinder back in the testing machine, and this technique is a methodology to extrapolate the buckling load before reaching the buckling load. So we apply first in the configuration of the test, we measure the frequencies. Then we apply a little bit of the load. We measure again the frequency. So we apply more load, we measure the frequency, and so on, arriving around 60–80% of the buckling load. Studying how the frequency changes of the structure, you can extrapolate the buckling load without reaching that. And this is a way to determine the buckling load without reaching it, but taking into account also the factors imperfection, because you can extrapolate and arrive to the real buckling load, not that one that you have to knock down with the factor of the imperfection and so on. Yeah, so it's related, you can look at some of the paper, but it's related really how this frequency, usually you look at the first frequency or the second one, but they shift during when a loading is applied. So you can put in a graph and extrapolate the buckling load.
One question I'm having. Are you able to hear me? This is Guru Prasad. Yeah, so I've worked on radio frequency welding of polymers.
Yeah,
so I just wanted to...
Yeah. One ply 0 degree, one ply 90, one ply 45.
And the variable stiffness, is it something analogous to the automated tape laying where
Yeah.
you can continuously vary?
Yeah.
Vary the orientation?
Yeah, you take a toe of fibers and you can change. A mill is done by automatic fiber placement.
Okay.
Yeah.
Okay. And a speculative question based on that. So now, is there a possibility of optimizing the tape layer so as to get a desired range of frequencies or a response? So we can optimize the tape layer to...
Yes, the idea is that you optimize this distribution of the variable of the stiffener, or how you place the toe, the variable changes. If you imagine one of the things that we did in another study, if you have a cutout for any reason, for instrumentation and so on, you can